Record, share screen. Yeah. You're going to think that what I start showing you and doing on the board is completely off topic and irrelevant, but I assure you that it's not. So today's the 19th. Hey, look. It came on. We're going to come back to it. As Micah pointed out, we did not come back to permutations, and I've decided that we're going to do the first two worksheets of this little unit because they're all about combinations, and combinations are tied into today's lesson as well, which is pretty cool. So there's some history here, which I'm not fully aware of, so I'm not going to like try to lie and make stuff up. I do know that Pascal's triangle is in relation to Blaise Pascal, a French mathematician. And honestly, people have written entire books about Pascal's triangle. So much cool math buried inside the triangle, but I'm not going to sit here and act like I know what it all is. So the primary application of it, though, is binomial expansion and something else that you're going to, I think, find nice. I hope. Be a little disappointed if we go through this and then you're like, oh, whatever, lame. Huh? Okay. Well, I hope I relight it today. Let's relight. That's right. To start Pascal's triangle, first off, you should center the number 1 on your paper. Make sure it's in the middle because the triangle is going to grow outwards in 2 directions like a big isosceles triangle. So to begin the triangle, I know it doesn't look like much of a triangle yet. You're just going to put the number 1. And now every row that we make after this will start with a 1 and end with a 1. And every term in the row will be the sum of the 2 numbers diagonally above it. That doesn't make any sense yet because there's not enough stuff. So for the next row, we're going to just put 1 and 1. Like I said, every row will start with a 1 and end with a 1, and every term, like on the inside of the row, will be the 2 numbers directly, like diagonally above it, added together. So this next row, you guessed it, is going to start with a 1. As I said, they all start with 1 and end with 1. Now, any number is going to be found by adding the 2 numbers diagonally up above it. So like I'm looking at this space right here. And so I have to look up diagonally this way and diagonally this way. What is 1 plus 1? So that space is going to be filled in with the number 2. And then I'm going to complete this row with 1. Still might not have a clue in the world what's going on. Like, how are we making this? It'll start to come together, I promise. As with every other row, the next row will start with a 1, and it will end with a 1. Now, this time, there are 2 spaces to fill in. And again, they're gotten by diagonally adding. So like if you add this number and this number, what is 1 plus 2? 3. So you're going to put a 3 in the space. Never, ever will you put a number directly below a number in the row right above it. They'll always be diagonally offset. And then, of course, the next one is a 3. Moving on to the next row. I think I'll start this one with a 1. Try something new. I think I'll end it with a, let's get crazy, a 1. Now, there are 3 empty spaces. What's the first one going to be right here? Next one? Next one? Now we're rocking. Good. Next row. Next row. Now, at this point, your triangle might start to look like it's flattening out like a blob of silly putty sitting on the desk on a warm day, it's going to start to like bulge out at the bottom. Because as the numbers now will start to grow and they'll start to get a lot bigger here in a few rows, then you need more space. And so you'll find yourself needing to leave a little more room for the girth. So next row, 1, end with a 1. And the missing numbers are what goes in between 1 and 6? What goes in between 6 and 15? What goes in between 15 and 20? 35. What goes in between 20 and 15? What goes between 15 and 6? And 6 and 1? Nice. You should see that every row, of course, has symmetry, right? There's going to either be one number in the middle that is like the middle divider, or there's going to be the same number twice in the middle, right? And then the left side and the right side are the same. So like in this last row right here, you can see like the 35s are the same. And then the symmetry on the outsides, do you see the 2171 going from the inside out? And that's the same on both sides. And every row possesses that characteristic. Like the row above it, the singular middle is 20. But again, these outsides are identical to each other. So that's going to just keep happening. Center, symmetric sides over and over again. Let's keep going until we get annoyed with this enough that we think we can't handle it anymore. Diedrich, what's this next row going to be? Nope.
Oh, stage. Wow.
Keep going.
No, could be 6.
Next one. Nice. Okay. Next one. Trinity, I want you to do this one. I want you to say them all in Spanish. Are you ready? Listo? Uno. Set.
36.
56. The next one, you just do 50 plus 20, which is 70. And then add the ends. 8 and 6 make 14. 70 and 14 make 84. You got these middle ones, Mullendor. I know you do. The two middle ones. Nice. And then, of course, the other side is just going to mimic. Once you get to the halfway point, the climb back down is simpler. It's ground already traversed. So keep going. Foxer, you want to help me with this next round? All right, let's go. Ready?
Oh. 45.
Yep. Ciento y veinte. 120. Perfecto, gracias. Y la próxima. I don't think so. I think if we do the 84 and the 126, again, my strategy when I do stuff like this, and this makes my life easier, is watch this magic trick. I erase this and I erase this, and I just do 80 plus 120. We can handle that, right? 80 plus 120 is obviously just 200. So then I know it's 200, but then I just add 4 plus 6. What's 4 plus 6? So I just add my 200 and my 10, and I get 210, right? That's how I add numbers in my head. I take off the ends and then put them back on. How about 126 plus another 126? Nope. 252. I'm going to get rid of this green one because it's kind of freaking me out. And then, of course, Boxer, now we can just work our way back down the hill. So 252 is like the top of the hill. Yeah, 210, 120, 5. We could keep going with this, but I don't really want to. I just want you to know that we could. I wanted to do now a math problem with you. You cool with that? Actually, I don't even care. Even if you're not, we're still going to do a math problem. So here it goes. Like, no, I mean, you do. You don't have to do it, but I think you'd probably want to. Here's our warm-up math problem for the day. Are you ready? I want you guys to do 9C4. Ready, go. We learned this yesterday. Good luck. I'm going to pour myself some fresh coffee while you labor through 9C4. Yeah, sure. Wherever. It's okay. Just wherever. Yeah. You don't have to add on to Pascal's triangle because I, aka the nicest guy you know, am going to provide you with a nice, neat printout of Pascal's triangle that goes all the way through the 16th row. It's kind of stuff I do. So nice. You have it already, Aubrey? What I got? What? Nope, you're off by 108. Oh, did you add 9, 2, and 7? That's kind of funny. Dope. Like you took the 2, 3, knocked the 6, then the 4, dropped the 8. Nice. It's a pretty logical way to do it, really. Did you guys get 126 or are you still working? Yep. For your second one, I want you to do 7C3. Hola. Bien. Hey, why was Santa's little helper so sad? No, because he had low self-esteem.
Why do basketball players like donuts?
I don't know.
Because they gotta dunk them.
I told you a perfectly good Christmas joke, and then you hit me with that.
I'm sorry.
Jeez. Hey, what does Mrs. Claus say to Santa Claus when there's a thunderstorm approaching? Looks like reindeer. Oh yeah, sorry, I was jerking around there. Yeah, second one. Oh, I'm recording, aren't I? Dang it. Well, at least there were good Christmas jokes, right? So we have 7 factorial over 3 factorial times 4 factorial. And again, I'm going to write out the 7 and the 6 and the 5. And then I'm only going to write out the 3, the 2, and the 1. The 3 and the 2 are going to go to 6. And this one is, yes, 35. Are you getting these right? I would hope. If not, is there anything I can clarify for you? It's just yesterday's lesson is all we're doing. And again, we had that moment yesterday where we realized that there's really no sense in writing out the full factorial on top because the big part of it is going to get knocked out by what we would have written on the bottom anyways. So we save time. Is everyone okay with 126 and 35? Okay. So I would like you to draw your attention back to Pascal's triangle. And so the first math problem that I asked you to do was 9C4. So at this point in time, I would direct your attention to Pascal's triangle and have you go down until you find the row that starts with a 9. And of course, I'm not talking about the dumb one. I'm talking about this right here. 9. You see it? So here we go. 1, 2, 3, jackpot. So 9C4 can be discovered right there in the belly of Pascal's triangle. Let's check and see if that couldn't actually possibly work again. Let's go to 7C3. So here is the row that starts with 7 right there. 1, 2, 3. Yeah. So right now, ready? Based on the Pascal's triangle that we have, what is 8C5? Go. It is 56. Very good. And that's a whale of a lot quicker than putting it into the formula, right? How about this one? What's 4C2? Good. Okay, how about 6C5? Good job. How about 8C4? Good job, you guys. So I wanted to show you that about Pascal's triangle, that, you know, there is a limit to this. The one I'm going to give you, I'm going to give you a copy of Pascal's triangle that's nice. It's nice and formatted, cool and everything. It goes down through 16 rows. But I will say, unless you feel like making a whole bunch more rows, this is not a very practical method. If I said like, what's 24C8, right? Like, I don't know of many people that have taken the time to make 24 rows of Pascal's triangle. I wouldn't either. As you can see from what I'm going to give you here in a minute, the numbers get really big, and only at the 16th row they get to the point where you're like, this is getting like hard to write. And then the 17th row, and then the 18th. I mean, they just keep growing. And so these are nice. So like if you find yourself in a math problem where it's like 5C3, just look at it and go, boom, 10. It takes like 1 second, if you know what I'm talking about. Okay, so that's what I want you to use Pascal's triangle for right now. When I first learned that, it really just kind of knocked my socks off. There occasionally in math, you find things where you just go, that's actually really neat. Like that is neat that is tied together like that actually works. And it has a ton of other applications, like I said earlier, but that's the one that's relevant to us right now. And it's really cool. So I'm going to hand out a couple things. The first one is the Pascal's triangle that I want you to have, and just keep it in your notebook if you'd be so kind. And then and you can use it as a resource for anything. I don't care. And then the second one is going to be an assignment that I want you to work on. Actually, 2 assignments. So yeah. I'm going to pause this and then I will unpause it if you guys have more questions. So let's do that. So the first problem on the decoder button, on the button page says, so the problem is E. And the problem is we're trying to solve for N. And so it says 4 factorial. You already have this on your worksheet. I'm just writing it down because I don't have it on a PDF right now. So what is 4 factorial? Do you have that one memorized? Yeah, it means 4 times 3 times 2 times 1. So in this case, we could simply say that N equals 24. And we're done with problem E. Now, I want to talk to you about some of the more difficult questions. And honestly, there's only a few of them. And again, as I always say, it's so tempting, like once I put work in front of you to just tune me out. But that's weird because then I'll just have to explain it again. So take a look down on the decoder button page, go all the way down to problem R. It's the 7th problem down, excuse me, 6th problem down. These, I have to go over this every time I hand this out, and I don't mind one bit, but why it's on this worksheet, I'm not entirely sure, but I do like this worksheet for other reasons. So I'm not going to white out part of it because then the joke won't make sense. So if I were to write this out, first off, I'm not looking for the answer to 6 times 5 factorial. Someone's asking me 6 times 5 factorial is the same as what factorial? Help me real quick. If you wrote this out, the thing I'm putting the red circle around, what would that say? No, I mean, like, what would it say? 5 times 4 times 3 times 2 times 1. And then if I take the 6 and I copy it down in front, what do you see right there in that box? You do. So the answer to this problem is 6. You're not looking for the math. If they wanted the answer, they would have put just equals n and you would have put 720 because that's what it actually equals. But they're saying this expression written like this is the same as what factorial, and that's why it's 6. So I would caution you that R, H, and L are the weird ones, and they're the ones where you're not looking for like a math answer. You're looking for what's it the same as, kind of. Those are always the hardest ones. Do you guys see anything else on that page that looks like it's going to get you? Anything else I could explain to you or help you with? You want to wait till you get there and then maybe you get stuck? Which one? Okay, let's take a look at problem I. Okay, so that's going to be the 4th problem down on the worksheet. You will see this several times. So problem I has us doing 3 factorial times 4 factorial. So the best way in the world for me to think of to explain this to you is let's just write them out. So what is 3 factorial? Right, unless you already know that it equals 6, right? There would be no harm in this case in just writing 6. Be clear? Like once you start to memorize your lower factorials, it's okay just in cases like this, just to jump right to it. Do you know what 4 factorial would be? Yeah, so you could either put as like defined 4, 3, 2, 1, or from you do. So from the very beginning, you could have just done 6 times 24, and that equals 144. Got it? So when you see 2 factorials stuck together like that, it's just a multiplication problem. Anything else catch your eye on that button page, the round one? Okay, the last thing is everybody go to that combination code page. If you'd be so kind, pretty please. There is going to come a point in this class, probably not this week, but where you're going to start to face the challenge of reading problems and wondering, is it a combination or a permutation? I can tell you that on this page, I mean, look at the name of the page. You see it? These are all combinations. So for every problem on this page, you can either use the NCR formula or you can use your Pascal's triangle to answer them all. Is that clear? All right, have at it. Get them done. I'm going to turn these into PDFs and put them online. And then I think that's it.